A very good morning, students. Today we are going to discuss about temperature distribution in solids and in laminar flow. We are discussing chapter 10, unit 4, which includes the heat transport, where today we are going to discuss about the heat conduction in a cooling fin. So as you know, the fins are generally used to enhance the mass transfer. These fins are used to increase the heat transfer area between a metal wall and the fluids, which gases having a low thermal conductivity. So the gases which having a low thermal conductivity, if it comes in contact with a metal surface, the heat transfer area must be increased because the thermal conductivity is less. So simple rectangular fin is shown in the figure. So you have seen a fin, this is nothing but the surface and this is nothing but the rectangular fin. So today we are going to find out how the heat conduction takes place through this fin. So we are going to consider the same figure for heat transfer. The wall temperature is Tw. The ambient air temperature is Ta. The fin length is L. Thickness is 2b. And the width is W. What we are going to assume is the heat losses from the end edges of the fin are negligible. Then we can apply the thermal energy balance over element of delta Z. So the shaded portion shows a delta Z. So we are going to apply this thermal energy balance only on the element delta Z. So what will be the terms which will comes into the balance will be the rate of thermal energy in. Rate of thermal energy in by conduction and rate of thermal energy out by conduction. So first of all we'll discuss these two terms and then we'll go for the convection. So a rate of thermal energy in by conduction will be nothing but, you can see it is Qz at Z. So this is heat flux, so you have to multiply by area. What will be the area through which you have to consider thermal energy in by conduction? So obviously it will be 2b thickness, is it right, into W. So 2b into width, W will be nothing but the area into heat transfer. What will be the thermal energy out by conduction? It will be again Qz at Z plus delta Z, obviously, into 2bW. So this will be the two terms for thermal energy by conduction. One more term that you have to consider here in thermal energy balance is rate of thermal energy out by convection. So convection means HA delta T. So see here, it is H and delta T is T minus TA. What is the area? Area you want to consider for convection will be the same shaded portion area above and below. So it will be 2W, is it right, into delta Z. That will be area into H delta T. So HA delta T will be the rate of thermal energy out by convection. Now you can combine all these terms as a thermal energy balance. 2bW Qz at Z minus 2bW Qz at Z plus delta Z minus H into 2W delta Z T minus TA. So this is a diagram where X, Y and Z coordinates are shown. Heat transfer in and out by conduction is shown. The thickness of the element is delta Z. L is the length of the fin, W is a width and 2b is a thickness. Now if you get this first thermal energy balance, what will be the next step? You have to divide this equation by 2bW into delta Z. If you divide it by, you will get equation of limit delta Z tends to 0, Qz at Z plus delta Z minus Qz upon delta Z is equal to minus h by b into t minus ta. So you can write the above equation of limit delta z tends to 0 as it is a definition of first derivative of qz. So it is a d by dz of qz is equal to minus h by capital B t minus ta. H is a heat transfer coefficient, qz is a heat transfer per unit area, B is nothing but the thickness, T is a temperature at any point, and Ta is nothing but the temperature of air. Now you can write the Fourier's law of heat conduction. Each Qz is equal to minus K into dt by dz. Can you write this in above equation? Yes. So what the equation becomes is minus K d square T by dz square is equal to h by b minus t minus ta. So you can write dt square d square t by dz square is h by kb into t minus ta. Now here we are introducing the boundary conditions and two dimensionless numbers. So the first boundary condition is at z is equal to 0. So z is equal to 0 means all surface. Temperature will be Tw. The second boundary condition z is equal to L means it is nothing but this corner. Z is equal to L. What you can write is, you can write dt by dz is equal to 0. What it mean? It means temperature remain constant. So that is mean. We are again introducing the two-dimensionless, three-dimensional quantity here. It is a somewhat complicated derivation. So listen carefully. Theta is ratio, dimensionless temperature ratio. So it is a T minus Ta upon Tw minus Ta. So Tw is a wall temperature, T is any temperature, and Ta is nothing but the temperature of air. The second dimensionless quantity is dimensionless distance. Why it is a dimensionless? Because there is no unit. Zeta is equal to Z by L. Z is a small, L is a total length. So Z by L will be dimensionless distance. The third will be called as a dimensionless heat transfer coefficient n square. N square is equal to HL square by KB. So n square is HL. So it means obviously heat transfer coefficient term is there, thermal conductivity is there. So from above equation, okay, so from this dimensionless temperature you can write T is equal to theta Tw minus Ta plus Ta. Okay, then equation can be written in terms of theta and zeta. So above equation we can write d square T by dz square can be write as d square theta upon L square into d zeta square. Tw minus Ta is equal to h by kb into t minus Ta. So this is how you can convert the above equations into the dimensionless quantity. Then what is the d square theta by d zeta square is, you can take L square this side, HL square by kb into t minus Ta upon Tw minus Ta. So this T minus Ta, Tw minus Ta can be written as theta. Is it right? HL square by kb, see here it is n square. So the right hand side become n square into theta is equal to d square theta by d zeta square. So you can solve this equation, and by solving this equation you know that you will get this equation as theta is equal to C1 e raised to n zeta plus C2 into e raised to minus n zeta. So now applying the first boundary condition. First boundary condition is got at z is equal to 0, Tw is equal to Ta. What is meant by theta is equal to? Theta is equal to 1. Why? Because Tw is Tw. Is it right? So theta is equal to 1. Okay, so you can put C1 plus C2 is equal to 1. Second boundary condition you can write that z is equal to L, dt by dz is equal to 0. So what will be zeta? Zeta is z by L, so it's equal to 1. The theta by dz is 0. Then by taking the first derivative of d theta by dz is equal to n into c1 e raised to n minus n into c2 into e raised to minus n. So equation 10.109. So this equation can be written like this, okay, is equal to this. If we take the first differential, d theta by dz is equal to 0 as per the above conditions. So the differentiation becomes nc1 e raised to n minus nc into e raised to 5. Solve this, you will get c2 is equal to c1 e raised to n minus e raised to minus n. Again put this equation in c1 plus c2 is equal to 1 and solve this. You will get the c1 value. c1 is equal to e raised to minus n upon e raised to minus n plus e raised to n. So this will be c2 and this will be c1. You can put c1 and c2 in theta and you can rearrange the terms. What you get? Theta is equal to e raised to n zeta minus 1 plus minus n e raised to minus n zeta minus 1 whole bracket upon 0 upon e raised to n plus e raised to minus n upon 2. If you remember, what is this? This will be a cos hyperbolic term. It is a cos hyperbolic of n zeta minus 1. The denominator is cos hyperbolic n. So this is how it gives a temperature distribution in a rectangular fin. It is a theta. Now what you want to find out is eta. What will be nothing but the effectiveness of the fin. So eta is called as the effectiveness of the fin and it is found out by the ratio of actual rate of heat loss from the fin. What is actual heat loss is occurring from the fin to the rate of heat loss from the isothermal fin. Means if the temperature of that fin remain constant, what will be the heat loss? That ratio is called as a effectiveness. Eta is equal to theta by theta max. So you can write again in terms of the double integration. Eta is equal to 0 to w 0 to L integration h into t minus t upon into dz minus dz into dy upon integration 0 to w integration 0 to L h into t w minus t dz into dy. So again you can put value of theta here as t minus t upon tw minus ta. You will get this equation cos hyperbolic n 1 minus zeta upon cos hyperbolic n. You will get this equation is cos hyperbolic n bracket minus 1 by n sin hyperbolic n into 1 minus zeta vary from 0 to 1. So put this condition and you will get eta is equal to tan hyperbolic of n upon n. What is n? N is equal to HL square by KB. So it is a dimensionless heat transfer coefficient. You can write HL square by KB. This is how you can find out the effectiveness of the fin. N is a dimensionless quantity defined by the equation. So we will discuss about the problem related to the rectangular fin and then we will go for the more problems. Problem 10.2. Calculate the heat loss from the rectangular fin for the following condition. Air temperature given 176.6 degrees Celsius. All temperature is 260. Thermal conductivity of fin is given. Thermal conductivity of air, heat transfer coefficient, length, width and thickness. All the values are provided to you. What you have to find out? What will be the heat loss? So you have to find out the thermal efficiency. Eta is given by eta is equal to tan hyperbolic n by n. You know what is n? N is HL square by KB. So tan hyperbolic of HL square by KB bracket square 1/2 upon HL square by KB raised to 1/2. So all values are provided to you: heat transfer coefficient value, length, thermal conductivity and breadth. All values are provided to you. You can find out what will be the eta is equal to 0.288. So this will be nothing but the effectiveness of the film, and heat loss through the rectangular fin is given by HA delta T. So H into delta T is TW minus T naught. Now you have to take a total temperature difference. You have to multiply it by eta because it is the effectiveness, and HA delta T, A will be 2W into L, not now delta Z, it will be 2B into L. So you can find out Q by 2W into L into H TW minus T naught into eta. You put all the values, you will get what will be the heat transfer rate in BTU per hour. Next, once you find out what is the thing but the heat transfer area, you can go for problem 10.3. An oil which is acting like a lubricant between the cylindrical surfaces. So one surface is moving, another surface is moving. Okay. Outer surface radius, inner surface radius is given, temperature is given. What you have to find out is what is nothing but the value of temperature, maximum temperature in coaxial cylinders. So all value of viscosity, density and thermal conductivity is given. What you can find out is omega. Omega is equal to 7908 into 2 pi by 60. You will get it in radians per seconds. You can find out B, mu, density rho, thermal conductivity, and you can put all these values in this equation. This equation will be T minus T naught is equal to 1/2 mu V naught square by K x by B bracket 1 minus x by B plus x by B. So all these values are nothing but in form of x by B, where x by B is given as a 1/2 and V naught is equal to written ohm into R. So putting all the value of radiant frequency x and B, is it 1.5? Okay, you can find out the Tmax. So similarly, the Tmax will be 79.3. It is 174.74. This is how you can find out nothing but the temperature, maximum temperature through the coaxial cylinders. Now the final we'll discuss about this problem and we'll stop it here. Consider a stainless steel pipe. What you have to find out? Having a diameter of 5 mm and length is 3 meter long. As current passing through the wire is 300 ampere and having a resistance of 0.125 ohm, the outer surface temperature is 450 Kelvin. The thermal conductivity is 20.5 watt per meter Kelvin. Estimate the maximum temperature rise through the wire. So what is given? R is given, thermal conductivity is given, TW is 450 degree, length is 3 meters, R is 2.5 millimeters and current density is 300 ampere. Now the heat produced per unit volume, if you want to find out, okay, it will be nothing but the SE. SE into volume, SE because unit is watt per meter centimeter cube into volume. So it will give you the power. Power is what? It is in terms of resistance and current density is I square by R is equal to SE into volume. What will be the volume? Will be a pi R square. Is it right? Into the length L. So from this you can find out value of the rate of heat production per unit volume, watt per centimeter cube. Once you find out, you can use the simple equation that we studied is T max minus TW is equal to SE into R square by 4K. you can again find out the maximum temperature. So this is how you can study all the topics from the 10 chapters, and you can do the exercise. So solve many problems related to the electric heat source, viscous heat source, and the heat conduction through the cooling film. Okay, these are the three important derivations and the problems generally asked in a examination. Okay, one more lecture we will conduct on the heat transfer, and then we will start the mass transfer operation. Thank you guys.